Okay, so this video is just going to show you some examples of how to find the volumes by cross-sections where they give you the shapes. So we're going to start off, let R be the region bounded by the x-axis in the curve y equals 2x minus x squared. So I included a little graph of this that you can see over to the right. So A says to determine the area of region R. Well, we need to know what R is, so hopefully you can see bounded by the x-axis in the curve is this shaded area right here. Well, we have to have an interval. Anytime we do areas or volumes, we must have an interval. And so to find this, if we've got the curve in the x-axis, we need to set them equal to each other to find out what that interval is. So we'll go 0 equals 2x minus x squared. Factor out an x, 2 minus x. X is 0 and 2. This is our 0 and this is our 2. And so when we did areas, we'd have to test to see who's on top. Well, you can see that right now, but we would go from 0 to 2, and we'd plug a number in, and if you plugged in 1, you get a positive, which is telling you that this y is on top. So area, we just have two dimensions, and we'd add up rectangles. So just a representative rectangle has a width of delta x and a height of f of x. And so we'd write our integral from 0 to 2. We'd want to add up a bunch of these rectangles. F of x, or in this case, there is no f of x given, but it'd be 2x minus x squared is our height, and our width is dx. And you can work this by hand. I'm going to go ahead and put it in the calculator just for the sake of speed. And this comes out to be 4/3. And that was area. So that was two dimensions. Alright, so now we're moving into the cross sections. Same R. It says the region R is the base of a solid. So solid sitting in this region. For this solid, the cross sections perpendicular to the x-axis are squares. So coming out at you are squares, and as to determine the volume of this. So again, I'm going to draw this representative rectangle. This is still delta x, and this is f of x, or our y. And so coming out at you, I'm just going to draw it so you can imagine what's happening. Coming out at you are squares, so we have to add that third dimension to figure out how high that is. So like we talked about before, since it's a square cross-section, this length should be the same as the bottom, another f of x, or y. So if we have to find the volume of one of those, we would have f of x times delta x, or f of x squared times delta x. That would be a single one of these rectangular prisms or square prisms. So if we wanted to add a bunch of them up, so we cover from 0 all the way to 2, we go from 0 to 2, f of x squared, and delta x becomes dx. So again, I was bad and put f of x, and there is no f of x defined, so I'm going to say f of x is the 2x minus x squared. Plug that into my calculator, and I get 16/15 as an answer, or 1.067. So that'll give me my volume. And something that you really have to understand when you start comparing these is it looks like this 4/3, this 1.333, is bigger than the 1.067. But you have to realize that they're different units completely. If area, it would be square feet or whatever that was, and for volume you would have cubic feet, which are different completely. So you cannot compare the area and the volume as far as the size there. Okay, so for C, the region R is the base of a solid, so we're putting another solid in here. But this time the cross sections perpendicular to the x-axis are isosceles right triangles. So we'll go back up here just to show you. And so now coming out, perpendicular to the x-axis, coming straight out at you, are isosceles right triangles. So there we have it. And so the cross section, what you should see is a triangle, a right triangle there. If you look through it, that was your isosceles right triangle. And since it's isosceles, the f of x and f of x are still supposed to be the same. So we talked about in the first video, if you're going to write the volume of one of these things, you do the area of the shape times the thickness. Okay, and our thickness of our rectangular shape is going to be our delta x here. So if we were doing the volume of one of these, the area of the shape is 1/2 base times height. It's a triangle, and then times our delta x. Well, in our drawing, our base was f of x, and our height was also f of x. Base f of x, height f of x. So our volume is going to be 1/2 f of x times f of x times delta x, where again f of x is equal to the 2x minus x squared. So if I wanted a bunch of these, I would go integrate from 0 to 2 of 1/2 f of x squared dx. And this should be half of the answer from letter B, because we're doing a triangle instead of the square. And so you should get 16 over 30 instead of 16 over 15, or 0.533 instead of 1.067. Alright, the last one, the region R is the base of a solid. Again, for this solid, the cross-sections perpendicular to the x-axis are semicircles. Okay, so I'm going to go sketch this in the drawing. So we've got semicircles coming out of this. So we still got the base being what it is, but we're going to put semicircles coming through. So if you were looking through this, the cross-section that you see is that semicircle right there. So the base of this would be the diameter of the semicircle, which is f of x. So if we went in here and did our area of the shape times our thickness, the area of a semicircle is 1/2 pi r squared, and our thickness is going to be delta x. Well, back from our drawing, we see that our diameter of our semicircle is f of x. So that must mean our radius is half of the f of x. So when we plug that in over here, we'd have 1/2 pi and then 1/2 f of x squared and delta x. So it is important that I put those parentheses in there because that's my radius and it has to get squared. So when we simplify this, we would square the 1/2 in here and get 1/4, and then we would multiply it by this 1/2 out front and we'd have a 1/8. Still have the pi, and we'd also have to square the f of x. So that would be one of these semicircles. So if we were going to do a bunch of them, we'd go from 0 to 2, and we'd do 1/8 pi f of x squared, and delta x would become dx. We talked about it may be a little easier, especially if you have to work these by hand. This is just a number. This can be brought out front, so this is the same integral. So if I bring out the 1/8 pi, I write it as pi over 8, 0 to 2 of f of x squared dx. If I go ahead and put that in my calculator, I get 2 pi over 15.